Good evening. So this is part 2 of our discussion of module 1.1, which is about digital systems and binary numbers. Before anything else, let us go back first. So I just want us to go back to this converting decimal to binary. But this is the method that we used last time. I will show you the usual or the common method. They're practically the same, but it's just the form that is different. For example, 41 base 10 in binary is 41. Base 10 in binary, we have already solved the equivalent, which is 101 0 1 0 1 101 0 0 1 101 0 0 1 base 2. So to find this binary equivalent, we divide by 2 in succession the number 41. Another way to write this is the usual division. So 41 divided by 2, that's 20, but you write the remainder on the right side. Remainder 1. Then 20 divided by 2. Make sure that you provide allowance space in the upper corner because we'll be filling it up. Let's move 41 here. 41 divided by 2, that's 20. Remainder is 1. Then 20 divided by 2, that's 10. Remainder is 0. 10 divided by 2, that's 5. Remainder 0. 5 divided by 2, that's 2. Remainder 1. 2 divided by 2, that's 1. Remainder 0. 1 divided by 2, that's 0. Remainder 1. And then take note of the remainders and read it from the latest to the least significant. So you read it from top to bottom or from latest to oldest. So that's 101 001 base 2. That's another way, which is practically the same, it's just that you write it this way. Another way of converting from decimal to binary. Now let's continue to complements of numbers. It says here that complements of numbers simplify the subtraction operation and for logical manipulation in digital computers. For example, you're trying to subtract in decimal, for example, 2 minus 4 equals negative 2 in decimal. We have the negative sign here. How are we going to implement this in binary? The binary equivalent of 2 is 10 minus, let's write the base 10. 2 is 10, 4 is 100, base 2. What would be the result in binary? 10 minus 100, our subtrahend is smaller compared to our minuend. How are we going to write negative 2? base 10. Negative 2 base 10 is what in binary? That's where the complement of numbers in binary is beneficial or is needed. Complements of numbers are simpler, less expensive circuits to implement the operations. Let's find out later. So there are two types of complements for each base R system. So the complement of a number actually is a general term. It is used in any base systems. The first type is the R's complement. RR is the radix or the base. R's complement or the radix complement, and then the R minus 1's complement or the diminished radix complement. It's not hard to remember because the word diminish itself means you subtract or you lessen. So the diminished radix complement is having a value that is less than the R's complement. I mean the value in terms of how it is called, because we are using R minus 1 instead of R, where R is the radix. For example, for base 2 or binary, we have the R's complement is called the 2's complement, while the R minus 1's complement or the diminished radix complement, that's 2 minus 1, so 1's complement. 2's complement and then 1's complement. For decimal, our base 10, our base radix is 10, so we replace R with 10. So we have the 10's complement and then R minus 1, so 10 minus 1, that's the 9's complement. So for hexadecimal, which is base 16, what is the R's complement and the R minus 1's complement? The base is 16, so our R is 16, so we have the 16's complement and then 15's complement. But what we are mostly concerned is in binary. So what we need in binary is the 2's complement and then the 1's complement. The 2's complement and the 1's complement. We have here the diminished radix complement or the R minus 1's complement. Wait. How to solve the diminished radix complement? The definition, let's read first the definition. The R minus 1's complement of n for a given number n of base R with n digits is equal to R to the n minus 1 minus n. Remember, R is the base and then n is the number of digits. Small letter n is the number of digits and capital N is the number itself. So remember this formula. To solve for the r minus 1, to solve for the r minus 1's complement, you just use the formula r to the n minus 1 minus n. This is the base or the radix. Then small letter n is the number of digits, and then capital N is the number itself. For example, what is the 9's complement of 546,700? This is the binary. In binary, I know. This is in decimal. 9's complement is the diminished radix complement in the decimal number system. Using this formula, our r is 10, and then our n is the number of digits. How many number of digits do we have here? 1, 2, 3, 4, 5, 6. So 10 to the n, which is 6. So 10 to the 6 minus 1, then minus the number itself, which is 546,700. The answer is 10 to the 6 is 1 million. 1 million minus 1, that's 999,999. So minus 546,700. The answer is 453,299 base 10. That is the 9's complement of 546,700. The 1's complement. The 1's complement of 101,1000. 1's complement is the diminished radix complement in the binary system. So using this formula, our base in binary is 2. Our n is the number of digits. How many digits are here? 1, 2, 3, 4, 5, 6, 7. So using this formula, our base 2 to the power of 7 minus 1 minus the number itself, which is 1011,000. The result is 1111111 minus the number. So the result is 0100111. It's easy, right? Next, let's solve for the let's read this first. The r minus 1's complement of octal or hexadecimal numbers is obtained by subtracting each digit from 7 or f, decimals 15 respectively. So can you see the pattern here? Can you see the pattern? For decimal, it's all for decimal, this r to the n minus 1 has all digits equal to 9. And how many 9's digits are here? 6. 9, 6 digits, where 6 is the number of digits. So that's 99 for decimal. For binary, r to the n minus 1 for binary is also 111 digits, with the number of ones equal to the number of digits. If there are 7 digits in the number, then you have 7 ones for the r to the n minus 1. That's for the decimal and binary. For octal, it says here that for octal, it is 7 and not 9 or 1, but 7. It is always the highest digit or the last digit for each number system. Just like for hexadecimal, we use F instead of 7 or 1 or 9. Let's have another example. Let's write an example. For example, for binary, we have the number 101011 base 2. Then for octal, we have 653 base 8. For decimal, we have 653. So we can use 653 base 10. For hexadecimal, let's use the same number but different base 16. We are going to solve for the diminished radix complement. R to the n minus 1. It's not clear. So r to the n minus 1 minus n. This is the formula for the diminished radix complement. We can use the formula or we can go directly. How many digits do we have here? 1, 2, 3, 4, 5, 6. 6 digits. So we write 6 ones. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Minus the number itself. 1, 0, 1, 1. So what is the result? 1, 1, 1, 1, 1, 1. Minus 1, 0, 1, 0, 1, 1. We subtract 0, 0, 1, 0, 1. There's not included. So the answer is 0, 1, 0, 1, 0, 0. This is the diminished radix complement of 101, 011. How about for octal? We have 1, 2, 3, 3 digits. For octal, we have 7, 7, 7, or 3. But remember that binary is base 2, octal is base 8, decimal base 10, hexadecimal base 16. 2 minus 1 is 1. That's why we have all ones here. The highest digit of binary is 1. For octal, the highest digit is 7. For decimal, that's 9. For hexadecimal, that's F, or 15 in decimal. So 3 digits, so we write down the highest, which are 3 digits, so 777 minus 653. What's that? It's 1, 2, and then 4, base 8. 653 in decimal, we used 9. So 3, 9 digits minus 653. So it's 3, 4, 6 base 10. Then this is the diminished radix complement of 653 in octal. This is the diminished radix complement of 653 base 10, which is in decimal. For the last one, we have 3 digits, so FFF minus FFF minus 653 will be the result to start here. F minus 3, that's 15 minus 3, so 12. What is 12 in hexadecimal? A is 10, so A, B, C, D, 10, 11, 12, A, B, C, 13, C. Wait, 10 is A, 10, 11, 12. We're looking for 12, so A, B, C. Yes. Let's see, and then F minus 5, so 15 minus 5, that's 10. 10 is A. Then 15, or F minus 6, that's 9. So 9A, C, base 16. This is the diminished radix complement of 653, base 16. If you are having a difficulty in memorizing this process, the simplified process, you can always stick to the formula. R is the base, and small digit n is the number of digits, then capital N is the number itself. Let's go to the radix complement, or the R's complement of an n-digit number n in base R. So the radix complement is just R to the n minus 1, R to the power small n minus capital N. So what's the difference? The difference is the negative 1. You don't use negative 1 anymore for the radix complement. It says here that this is obtained by adding 1 to the R minus 1's complement. Yeah. Since R to the n minus 1 is R to the n minus 1 minus n plus 1. You can obtain the radix complement from the diminished radix complement by adding 1 to it. For example, the tens complement of a decimal 2389 is 7610 plus 1 equals 7611, and is obtained by adding 1 to the nines complement value. Did we have an example on that? The two's complement of binary 101100 is 010011 plus 1, and is equal to 010100, and is obtained by adding 1 to the ones complement value. You can use the formula directly. You can use this formula, or you can use this formula directly, or you can compute for the diminished radix complement and just add 1 to it. For example, what is the radix complement of this numbers? Solve for the radix complement of these numbers. Let's write this 1, 2, 3, 4. For number 1, the radix complement of 101011 base 2, that would be Wait. Let me write it clearly. These values are the r to the n minus 1 or the diminished Radix Complement. The Radix Complement, we will solve them. For number 1, the Radix Complement of this number is the diminished Radix Complement 0, 1, 0, 1, 0, 0, base 2 plus 1, so that is 0, 1, 0, 1, 0, 1, base 2. This is the Radix Complement, or the 2's complement. This is the 1's complement, since we are in binary. For number 2, the Radix Complement of 653 base 8 is 124 base 8 plus 1, so that's 125 base 8. For number 3, the 2's complement of 653 base 10 is 346 base 10 plus 1, that is 347 base 10. For number 4, the 2's complement of 653 base 16 is 9ac base 16 plus 1. So what is c plus 1? So d. So 9ad base 16. So these are the 2's complement, or the Radix Complement, while this are the diminished Radix Complement or 1's complement, since we are in binary number system. So try to read these other examples. Let's try this. The 10's complement of 246,700. 10's complement. This is the Radix Complement. 9's complement is the diminished Radix Complement if you're talking in the decimal number system. 10's complement of 246. Let's try to solve the 10's complement of this decimal number 246,700. We can use the formula directly, r to the n minus n. So that's base 10, 10 to the 1, 2, 3, 4, 5, 6, 6 digits. So 10 to the 6 minus the number itself, 246,700. That is 1,000,000 minus 246,700. Then if we use the other method, r to the n minus 1 minus n plus 1. Will this be easier? R to the n minus 1 for base 10. Recall that for decimal, we write 9999 depending on the number of digits. For 1, 2, 3, 4, 5, 6, there are 6 digits, so we write 6, 9 digits. 1, 2, 3, 4, 5, 6. 999 minus the number itself. which is 2, 4, 6, 700 plus 1. So this is much easier, right, compared to this, when you're compared to this, wherein you are dealing with a lot of zeros and you will have to borrow and borrow, since these are all zeros. But if we use this diminished Radix Complement, the digits are all in 999, so it's easy for us to subtract. So 9, 9, 2, 3, then 5, then 7, then we add 1. We add 1. It's 10 carry 1, 10 carry 1, 2, 3, 3, 5, 7. So the answer is 753,300, which is correct. 753,300. So which is easier, this one using the formula, or if we use the diminished Radix Complement, then just add 1? I think this is much easier compared to this. Should have the same answer, since negative 1 and plus 1 will just cancel, so it will just go back to this equation. We are done with the Radix Complement and the diminished Radix Complement. Let's go to the process of subtraction with complements. What's the next? Subtraction with complements. This is the process. First is we add the minuend m to the r's complement of the subtrahend n. Mathematically, that would be m plus, diba, if we subtract, we have the minuend and the subtrahend. The minuend is the upper number where we subtract from, and the subtrahend is the number that we are subtracting. Subtracting from the minuend. So add the minuend m to the r's complement. R's complement, not the diminished Radix Complement. Add the minuend to the r's complement of the subtrahend n. Mathematically, that's m plus. So you get the, first is you need to get the r's complement of the subtrahend, and that is using this formula, r to the n minus 1. Then if m is greater than n, the sum will produce an n carry. I don't like this too long explanation. Let's just see the example. So for the example here is a decimal, is in decimal system, so the r's complement is the tens complement. We have the subtrahend, we have the minuend and then the subtrahend. So it's said in the procedure to get the r's complement of the subtrahend. What is the r's complement of 3 to 50? The tens complement of 3 to 50. is equal to, there are 4 digits, so 9999 minus 3250. So 9, 4, 7, and 4, 7, 6 plus 1. It's 10 carry 1, 4, 5. So 6,750 base 10. That is our tens complement. So 967. Huh? That happened. 96750. Tens complement of n. Ooh, right. Where did we? Be careful of this. Be careful of the number of digits. 1, 2, 3, 4, 5. 7, 2, 5, 3, 2. This has 5 digits. While 3 to 50, this has 4 digits. So you need to use the number of digits of the bigger number. So this is wrong. In solving the tens complement, it should be 9, 9, 9, 9, 9. 9. There should be, it should have 5 digits minus 3 to 50. Be 9, 4, 7, 6, 9. 10 plus 1. So 0 carry 1. 0 carry 1, 4, 5, 7, 9, 6. So 9, 6, 7, 50. This should be the right answer, the right tens complement. This is the tens complement of this 5-digit number. That's why it wrote here 96750. 96750. So you add after adding, you add the result. You add a tens complement to the minuend. The minuend is 72532. Seven to 532 plus the tens complement. We have the sum. Then the next rule is to determine if m is greater than n or m is less than n. If m is greater than n, if the minuend is greater than n, we discard the end carry. But if n is less than n, the sum doesn't produce an end carry is equal to, which is the r's complement. And to obtain the answer in a familiar form, take the r's complement of the sum, place a negative sign in front. It will be much easier if m is greater than n. But if m is, or the minuend is less than n, we have to take the r's complement of the sum and place a negative sign in front. Negative sign is indicated with, let's see. So in this example, our minuend is greater than n. So we just discard the end carry and take the answer which is 69282. The answer is 69282. Note that m has 5 digits. Yeah, I've already explained this one. M has 5 digits while n has only 4 digits. Both numbers must have the same number of digits, so write n equals 0 to 250. Just like what we did here. We added 0. Both digits must have the same number of digits. Both numbers must have the same number of digits. Since m is greater than n, the result is therefore positive. Another example. This example is in binary. So given the two binary numbers x and y equals this, perform subtraction x minus y and y minus x by using 2's complement. So let's solve. Let's take a break. Let's explain it on the next part 3.